Beneath the waves that cover more than 70% of our planet lies a realm so vast, so unexplored, and so profoundly mysterious that it challenges everything we think we know about human history, civilization, and life itself. The ocean depths hold secrets that have remained hidden for millennia, stories written in stone and sediment, waiting patiently for those brave enough to descend into the darkness and read what has been preserved in the cold embrace of the sea. This is not merely a tale of sunken ships or lost treasure, though those elements certainly play their part in our narrative. This is a story about the very foundations of human civilization, about cities that thrived when our ancestors were still learning to cultivate the land, about structures so ancient and so enigmatic that they force us to reconsider the timeline of human achievement we have so carefully constructed over centuries of archaeological study. The underwater world presents a paradox to modern science. We have mapped the surface of Mars with greater detail than we have charted our own ocean floors. We have sent probes to the outer reaches of our solar system, yet the deepest trenches of our seas remain largely unexplored, their contents unknown, their secrets preserved in crushing pressure and absolute darkness. When we do venture into these depths, when we send our submersibles and our remotely operated vehicles into the abyss, we consistently find things that surprise us, that challenge our understanding, that open new chapters in the story of our planet and our species. Ancient hunting grounds submerged beneath freshwater lakes, entire cities swallowed by rising seas, architectural marvels that predate the pyramids, and geological formations so perfectly structured that they blur the line between natural phenomenon and human construction. The deep ocean is not just a graveyard for lost civilizations and tragic maritime disasters. It is a living, breathing ecosystem of unimaginable complexity and diversity. In the perpetual night of the deepest trenches, life has found ways to not merely survive but to thrive, evolving into forms so alien and so specialized that they seem to belong to another world entirely. Creatures of the deep have developed strategies for existence that operate on principles fundamentally different from those we observe in the sunlit surface waters. They have learned to navigate in total darkness, to withstand pressures that would instantly crush any surface-dwelling organism, to find sustenance in an environment where traditional food chains simply cannot exist. And even deeper still, beneath the very seafloor itself, scientists have discovered entire ecosystems of microorganisms living in the cracks and fissures of volcanic rock, feeding not on the energy of the sun, but on the chemical reactions produced by the Earth itself. The story we are about to explore spans thousands of years and encompasses the full breadth of our planet's oceans, from the relatively shallow continental shelves where ancient cities still stand in silent testimony to vanished civilizations, to the deepest trenches where the very crust of the Earth is being recycled in the slow dance of tectonic plates. We will examine evidence that challenges conventional archaeological timelines, investigate maritime mysteries that governments have attempted to seal away from public scrutiny, and explore the cutting edge of marine biology where each expedition into the deep brings new discoveries that rewrite our understanding of what life is and where it can exist. This is a journey into the last true frontier on Earth, a realm where history, mystery, and science converge in ways both beautiful and unsettling. The submerged landscape of our world holds clues to climate changes so dramatic they reshaped coastlines and forced entire populations to flee or perish. When the last ice age ended approximately 12,000 years ago, sea levels rose dramatically as vast continental ice sheets melted and returned their frozen water to the oceans. This process did not happen overnight, but in geological terms, it was remarkably swift. Coastlines that had been inhabited for thousands of years were inundated, and the people who lived there had to adapt, migrate, or face extinction. The archaeological evidence of their existence, their settlements, their hunting grounds, and their sacred sites were submerged beneath meters or even hundreds of meters of water, preserved in some cases with remarkable fidelity by the very waters that consumed them. For modern archaeologists, these submerged sites represent a unique window into a period of human history that is poorly understood through terrestrial archaeology alone, a time when our ancestors were making the crucial transition from nomadic hunter-gatherers to settled agricultural communities. In the cold, clear waters of Lake Huron, one of the great freshwater seas of the North American continent, researchers have discovered evidence of human activity that dates back 10,000 years, to a time when the lake levels were much lower than they are today, and what is now underwater was once dry land traversed by both humans and the animals they hunted. The Alpina Amberley Ridge, now submerged beneath the modern lake, was once a natural corridor used by migrating caribou, and the humans who depended on these animals for survival recognized this and exploited it with remarkable ingenuity. The discovery of obsidian flakes, the telltale remnants of stone tool manufacturing, scattered across this now submerged landscape, has revealed the presence of ancient hunting structures, carefully constructed lines of rocks and posts designed to funnel the migrating caribou towards specific killing zones where hunters could dispatch them with maximum efficiency. These underwater archaeological sites in Lake Huron are providing researchers with unprecedented insight into the hunting strategies and social organization of Paleo-Indian cultures that existed in this region during the early Holocene period. The preservation of these sites is extraordinary because the cold, freshwater environment of the lake has prevented the kind of decay and degradation that typically destroys organic materials at terrestrial archaeological sites of comparable age. Wooden posts that would have rotted away millennia ago on dry land are still standing in their original positions beneath the waters of Lake Huron, marking out the geometry of ancient hunting structures with perfect clarity. Researchers using sonar mapping and remotely operated vehicles have been able to create detailed three-dimensional maps of these sites, revealing patterns and structures that would be impossible to detect through conventional archaeological excavation methods. The hunting structures themselves demonstrate a sophisticated understanding of animal behavior and landscape management that challenges simplistic notions of Paleo-Indian societies as primitive or unsophisticated. These were not random arrangements of stones or opportunistic ambush sites, but carefully planned and constructed facilities that required significant labor investment and implied a level of social organization capable of coordinating the efforts of multiple family groups or bands. The placement of the structures takes advantage of natural topographic features to maximize their effectiveness, funneling the caribou along specific paths that led inevitably toward the waiting hunters. Some of the structures include what appear to be blinds or hiding places where hunters could conceal themselves while waiting for the game to approach, suggesting a patient, strategic approach to hunting rather than the chaotic pursuit often depicted in popular representations of prehistoric hunting. The obsidian flakes found at these sites are particularly significant because obsidian, a volcanic glass prized for its ability to be worked into extremely sharp cutting tools, is not native to the Lake Huron region. The nearest sources of obsidian are located hundreds of kilometers away, which means that the people who hunted on the Alpina Amberley Ridge were either traveling great distances to obtain this material or were participating in long-distance trade networks that connected communities across vast stretches of the North American continent. Either scenario implies a level of social complexity and intergroup interaction that goes far beyond the isolated nomadic bands often imagined in reconstructions of Paleo-Indian life. These people were connected to broader regional and perhaps even continental networks of exchange and interaction, sharing not just material goods, but also information, ideas, and possibly even genetic material as groups intermarried and formed alliances. The study of these submerged archaeological sites requires specialized equipment and training that goes well beyond the skill set of traditional terrestrial archaeologists. Underwater archaeology is a demanding discipline that combines the intellectual rigor of conventional archaeology with the technical expertise of professional diving and the engineering knowledge required to operate sophisticated remote sensing equipment. Researchers must be able to work in environments where visibility may be severely limited, where currents can make maneuvering difficult, and where the cold water can quickly lead to hypothermia if proper precautions are not taken. They must be able to interpret sonar images and photogrammetric data, translating the electronic signals and digital photographs into meaningful archaeological information. And they must be able to work with preservation and conservation specialists to ensure that artifacts recovered from underwater contexts are properly stabilized and treated to prevent deterioration once they are exposed to air. The underwater landscape of Lake Huron is just one example of how changing water levels over the course of human history have preserved archaeological sites in aquatic contexts. Similar discoveries have been made in lakes, rivers, and coastal waters around the world, each contributing to our understanding of how our ancestors lived, hunted, built their communities, and adapted to changing environmental conditions. In Europe, researchers have discovered submerged settlements in alpine lakes that provide exquisitely detailed evidence of Neolithic and Bronze Age life, with organic materials preserved in the oxygen-poor sediments of the lake bottoms. In the coastal waters of the Mediterranean, divers have explored submerged harbor facilities and coastal settlements that document the maritime trade networks that connected ancient civilizations. And in the shallow seas that now cover what were once vast coastal plains, researchers are beginning to find evidence of human occupation dating back to the last ice age and beyond, suggesting that sea level rise may have inundated some of the most densely populated and culturally significant landscapes of the prehistoric world. The implications of these discoveries for our understanding of human history are profound. If some of the most important centers of early human civilization were located in coastal areas that are now underwater, then our archaeological record is necessarily incomplete and potentially quite biased toward inland sites that happen to remain above water as sea levels rose. The conventional narrative of human cultural evolution, with its emphasis on the development of agriculture in river valleys and highland plateaus, may need to be substantially revised to account for the possibility that equally or even more advanced societies were flourishing in coastal lowlands that are now inaccessible to conventional archaeological investigation. This is not to suggest that we must abandon everything we think we know about human prehistory, but rather that we should approach our existing knowledge with appropriate humility and remain open to the possibility that major discoveries yet to be made beneath the waves may fundamentally alter our understanding of where and when complex societies first emerged. The Mediterranean Sea, that great crossroads of ancient civilizations, cradle of Western culture and birthplace of so many of the political, philosophical, and artistic traditions that continue to shape our world today, holds within its depths the remnants of cities and harbors that once teemed with life and commerce. The sea has been both highway and barrier throughout human history, facilitating trade and cultural exchange while also presenting formidable obstacles to communication and transportation. The peoples of the Mediterranean learned early to master maritime technology, developing ships capable of crossing hundreds of kilometers of open water, navigational techniques that allowed them to find their way even when out of sight of land, and trading networks that connected communities from the Levant to the Pillars of Hercules and beyond. These maritime civilizations left their mark not just in the written records and monumental architecture that have survived on land, but also in the underwater archaeological sites scattered across the Mediterranean seafloor. Off the southern coast of Greece, in the azure waters of the Laconian Gulf, lies one of the most remarkable and well-preserved examples of a Bronze Age settlement anywhere in the world. Pavlopetri, as this submerged city is known, dates back approximately 5,000 years to a period when the great palace civilizations of Minoan Crete and Mycenaean Greece were beginning to emerge as dominant powers in the eastern Mediterranean. Unlike many underwater archaeological sites that consist of scattered artifacts or isolated structural remains, Pavlopetri is a complete town, with streets, buildings, courtyards, tombs, and even what appear to be religious or ceremonial structures all preserved in their original spatial relationships. The site was first discovered in the 1960s by an oceanographer who was conducting a coastal survey and noticed what appeared to be geometric shapes and linear features on the seafloor. Subsequent investigations by archaeologists confirmed that these were indeed the remains of an ancient settlement, and systematic mapping efforts have since revealed the full extent and complexity of this remarkable site. The preservation of Pavlopetri is extraordinary because the city appears to have been submerged gradually and relatively peacefully rather than destroyed by some catastrophic event. There is no evidence of the kind of destruction layers typically associated with warfare or natural disasters. Instead, the buildings and streets simply sank beneath the rising waters, possibly as a result of tectonic subsidence combined with sea level rise in the aftermath of the last ice age. This gentle submergence meant that the structural layout of the city remained largely intact, providing archaeologists with a snapshot of Bronze Age urban planning and architecture that is unparalleled in its completeness. The streets of Pavlopetri are still clearly visible, laid out in a roughly orthogonal grid pattern that suggests some degree of central planning or at least commonly accepted conventions for organizing urban space. The buildings vary in size and complexity, from small single-room structures that were probably ordinary dwellings to larger, more elaborate buildings that may have served administrative, religious, or elite residential functions. The archaeological team that has been studying Pavlopetri has employed a range of advanced technologies to map and document the site without disturbing the delicate remains. Using sonar scanning, underwater photography, and photogrammetric modeling, researchers have created detailed three-dimensional representations of the entire site that allow them to study the spatial relationships between different structures and to identify patterns in the layout and organization of the city. These digital models have revealed features that would be difficult or impossible to recognize through conventional underwater survey techniques, such as the subtle differences in building construction techniques that might indicate different periods of occupation or different functional uses for various structures. The research team has also been able to identify areas where erosion or other taphonomic processes have damaged or destroyed parts of the site, allowing them to prioritize areas for more intensive study or potential excavation. One of the most intriguing aspects of Pavlopetri is the evidence it provides for the maritime economy and culture of Bronze Age Greece. The location of the city, on a now submerged peninsula that would have provided excellent natural harbors and commanding views of the surrounding sea lanes, suggests that it was positioned to take advantage of maritime trade routes connecting the Greek mainland with Crete, the Cycladic Islands, and the broader eastern Mediterranean world. Artifacts recovered from the site include pottery that can be stylistically linked to various regions of the Mediterranean, indicating that Pavlopetri was part of the extensive trade networks that characterized the Bronze Age economy. The people who lived in this city were not isolated or provincial, but were engaged with the broader currents of culture, commerce, and possibly politics that flowed through the Mediterranean world during this pivotal period in human history. The buildings of Pavlopetri provide valuable evidence for domestic architecture and daily life in Bronze Age Greece, a topic about which we have relatively limited information from terrestrial sites where structural remains are often poorly preserved or have been heavily disturbed by later occupation and construction. The houses at Pavlopetri appear to have been constructed using stone foundations with upper walls made from mud brick or other perishable materials that have not survived the millennia of submersion. The layout of these houses typically includes several rooms arranged around a central courtyard, a design that appears frequently in Mediterranean architecture, and that provides excellent ventilation and natural lighting while also offering privacy and protection from the elements. Some of the larger buildings have what appear to be storage facilities, suggesting that individual households were engaged in agricultural production and needed space to store surpluses of grain, olive oil, wine, or other commodities. The tombs at Pavlopetri are particularly significant for understanding Bronze Age burial practices and beliefs about death and the afterlife. The graves that have been identified at the site appear to be chamber tombs cut into the bedrock or constructed from stone slabs, similar to burial practices documented at other Bronze Age sites in Greece and the Aegean. The inclusion of grave goods with the burials, including pottery vessels, bronze implements, and personal ornaments, suggests that the people of Pavlopetri believed in some form of afterlife, or at least felt it was important to provide the deceased with objects that had been meaningful to them in life, or that might be useful in whatever existence awaited them beyond death. The location of the cemetery in relation to the residential areas of the city may also provide clues about social organization and kinship structures, with different tomb clusters potentially representing different family groups or lineages. The discovery and study of Pavlopetri have contributed significantly to our understanding of Bronze Age urbanism and have raised important questions about how we define and recognize cities in the archaeological record. The site demonstrates that complex urban settlements existed in the Aegean region much earlier than previously thought, and that these settlements exhibited sophisticated planning and organization. The grid-like street layout, the differentiation of building types and functions, and the presence of what appear to be public or communal spaces all suggest that the inhabitants of Pavlopetri had developed social and political institutions capable of managing urban life and coordinating the activities of a relatively large and diverse population. This challenges the notion that urbanism in Greece was primarily a development of the classical period and suggests that the roots of Greek urban culture extend much deeper into the past. The fact that Pavlopetri is underwater actually provides some advantages for archaeological research, despite the obvious challenges of working in a submerged environment. The site has been protected from the kind of agricultural activity, urban development, and deliberate quarrying that have damaged or destroyed so many terrestrial archaeological sites. The ancient stones have not been recycled into later buildings, the streets have not been plowed over or paved with modern roads, and the graves have not been looted by treasure hunters. The site exists in a kind of time capsule preserved by the sea that claimed it. However, this protection is not absolute. Marine organisms can damage stone structures, currents can erode features and disperse artifacts, and modern activities like fishing and recreational diving can inadvertently cause damage. There is also the ever-present threat that rising sea levels and increasing storm intensity associated with climate change may accelerate the deterioration of the site, creating an urgent need to document and study Pavlopetri before it is damaged beyond recovery. The research team working at Pavlopetri has been acutely aware of these preservation challenges and has made the documentation and protection of the site a top priority. In addition to creating detailed maps and three-dimensional models, the team has worked with local authorities to establish protective regulations that limit access to the site and prohibit activities that might cause damage. They have also engaged in public outreach and education efforts to raise awareness about the significance of the site and the need to protect it for future generations. These efforts have included creating virtual reality experiences that allow people to explore the submerged city without physically visiting the site, producing educational materials for schools and museums, and working with documentary filmmakers to bring the story of Pavlopetri to a wider audience. Through these initiatives, the researchers hope to foster a sense of shared ownership and responsibility for this remarkable archaeological treasure, ensuring that it will be preserved and studied for years to come. Moving from the Mediterranean to the waters of the Western Pacific, we encounter archaeological controversies of a very different nature, sites that challenge not just the details of our historical understanding, but the very foundations of how we think about ancient civilizations and their capabilities. The waters surrounding the Japanese island of Yonaguni, the westernmost inhabited island of Japan, located just over 100 kilometers from Taiwan, have become the focus of intense debate among archaeologists, geologists, and alternative history enthusiasts due to the presence of a massive underwater stone formation known as the Yonaguni Monument. This structure, which was first discovered by a local dive tour operator in the mid-1980s while searching for new locations where divers could observe hammerhead sharks, consists of a series of massive stone platforms, walls, and what appear to be carved features including steps, terraces, and right-angle formations that seem almost impossibly regular and geometric to be the product of natural geological processes. The Yonaguni Monument has become a lightning rod for controversy because it sits at the intersection of several different academic disciplines and theoretical perspectives, each with their own methodologies, assumptions, and standards of evidence. On one side of the debate are those who see in the structure evidence of a lost civilization, a technologically advanced society that existed in the prehistoric past and was subsequently destroyed by rising sea levels or some other catastrophe, leaving behind only enigmatic monuments that mainstream archaeology has failed to properly recognize or investigate. These researchers and writers often connect the Yonaguni Monument to other controversial archaeological sites and to legendary accounts of lost civilizations like Atlantis or the hypothesized Pacific civilization of Mu, which was proposed in the 19th century as a Pacific equivalent to Atlantis based on a misinterpretation of ancient Mayan texts. On the other side of the debate are academic archaeologists and geologists who argue that the Yonaguni Monument is a natural rock formation, the product of well-understood geological processes including erosion, fracturing, and mass wasting that can create remarkably regular and geometric features in certain types of sedimentary rock. The physical characteristics of the Yonaguni Monument are undeniably impressive and at first glance do seem to suggest artificial construction. The main structure consists of a massive rectangular platform approximately 50 meters long and 20 meters wide, with vertical walls that drop approximately 25 meters to the seafloor. These walls are remarkably flat and straight, with sharp corners and edges that create near-perfect right angles. The surface of the platform is crossed by what appear to be channels or grooves, some of which form geometric patterns. At various points on the structure are features that look like steps or terraces, with horizontal surfaces and vertical risers that create a staircase-like appearance. There are also what some observers have interpreted as carved faces, symbolic representations, or even writing, though these interpretations are highly controversial and most academic specialists who have examined the supposed carvings see nothing more than natural weathering patterns and the psychological tendency of humans to perceive meaningful patterns in random or ambiguous stimuli. The geological context of the Yonaguni Monument is crucial for understanding how it formed and whether it is natural or artificial. The structure is carved from a type of sedimentary rock known as sandstone, which forms in horizontal layers as sand is deposited and then compressed and cemented over geological time. This layered structure is characteristic of sedimentary rocks and creates natural planes of weakness along which the rock can fracture or cleave when subjected to stress. When sandstone formations are exposed to weathering and erosion, these planes of weakness can produce remarkably geometric features including flat surfaces, straight edges, and right-angle corners. Additionally, sandstone formations are often cut by vertical fractures called joints, which form as the rock is subjected to tectonic stresses or as it expands and contracts in response to changes in temperature and pressure. When erosion exploits both the horizontal bedding planes and the vertical joints, it can create stepped or terraced features that closely resemble artificial construction. Geologists who have examined the Yonaguni Monument have pointed to numerous features that are consistent with natural formation and that would be unusual or unexpected if the structure were artificially constructed. These include the fact that the supposed steps and terraces do not form a consistent or regular pattern, as one would expect if they were intentionally designed for human use, but instead vary considerably in height and depth. There are also tool marks or other clear evidence of quarrying or stone shaping, which would be expected if the monument were carved from living rock by human hands. The rock surfaces show natural weathering patterns and are covered with marine organisms, with no clear boundary between worked and unworked stone that would be expected at an artificial structure. Furthermore, similar geometric rock formations are known from terrestrial locations on Yonaguni and other nearby islands, suggesting that the underwater formation is simply an example of the same natural geological processes operating in a submarine environment. However, those who argue for an artificial origin for the Yonaguni Monument point to certain features that they claim cannot be easily explained by natural processes. These include what appear to be drainage channels or gutters, circular depressions that might have been post holes for wooden structures, and a large roughly spherical stone that sits near the monument and that some interpret as a carved sphere or megalithic ball, similar to those found at some archaeological sites in Central and South America. They also argue that the statistical probability of natural processes producing such a concentration of geometric features in a single location is vanishingly small, and that the most parsimonious explanation is that at least some modification or enhancement of natural rock formations was carried out by humans. Some proponents of the artificial origin theory suggest that the monument might have been a natural formation that was recognized and utilized by ancient people, who then carved or enhanced certain features to make it more suitable for ceremonial or practical purposes. The dating of the Yonaguni Monument is another area of significant controversy. If the structure is artificial, determining when it was built is crucial for understanding what civilization created it and what level of technological and social sophistication would have been required. The depth at which the monument sits, approximately 25 meters below the current sea level, means that it would have been above water during the last ice age when sea levels were significantly lower than they are today. Based on sea level curves that chart the rise of the oceans as the ice sheets melted, the monument would have been submerged approximately 10,000 years ago, which means that if it is artificial, it would predate the oldest known monumental architecture in the archaeological record by several millennia. This is one of the reasons why mainstream archaeologists are skeptical of the artificial origin theory, as it would require us to accept that there was a civilization capable of megalithic construction at a time when most human societies were still engaged in hunting and gathering, and had not yet developed agriculture, permanent settlements, or complex social hierarchies. Proponents of the lost civilization theory argue that this chronological problem is precisely why the Yonaguni Monument is so significant. They suggest that there were advanced civilizations in the distant past that we know nothing about because their remains are now underwater or have been destroyed by geological processes. They point to other controversial sites around the world, including the ruins discovered in the Gulf of Khambhat off the coast of India, structures on the Mediterranean seafloor, and various terrestrial megalithic sites that have proven difficult to date using conventional archaeological methods. They argue that mainstream archaeology is constrained by a paradigm that assumes a linear progression of cultural development from simple to complex, and that this paradigm prevents researchers from seriously considering evidence that might challenge conventional timelines. They call for more open-minded investigation of anomalous sites and greater willingness to entertain alternative interpretations of the archaeological record. Academic archaeologists respond that extraordinary claims require extraordinary evidence, and that the burden of proof lies with those who propose radical revisions to established historical frameworks. They argue that the Yonaguni Monument can be adequately explained by natural geological processes, and that there is no compelling reason to invoke lost civilizations or advanced prehistoric cultures when more prosaic explanations are available. They also note that many of the features cited as evidence of artificial construction are ambiguous at best, and that selective photography and videography can make natural formations appear more regular and geometric than they actually are when viewed in person or from multiple angles. They emphasize the importance of rigorous scientific methodology, including systematic survey and excavation, detailed geological analysis, and careful consideration of alternative hypotheses before concluding that any particular site represents evidence of human activity. The debate over the Yonaguni Monument remains unresolved and continues to generate heated discussion in both academic and popular forums. The site has been featured in numerous television documentaries, many of which present it as evidence of lost civilizations or ancient mysteries, often with dramatic music and narration that emphasizes the supposedly inexplicable nature of the formation. These presentations tend to downplay or ignore the explanations offered by geologists and archaeologists who have studied the site, instead focusing on the opinions of researchers who support the artificial origin theory. This has created a situation where popular perception of the Yonaguni Monument is often at odds with the consensus view of academic specialists, contributing to a broader cultural phenomenon in which alternative historical narratives find enthusiastic audiences despite lacking support from mainstream scholarship. One of the challenges in resolving debates like the one surrounding the Yonaguni Monument is that underwater archaeology is expensive, technically demanding, and logistically complex, which means that many potentially significant sites remain understudied or entirely uninvestigated. Unlike terrestrial archaeological sites, which can often be excavated using relatively simple equipment and straightforward field methods, underwater sites require specialized diving equipment, remotely operated vehicles, sophisticated mapping and imaging technology, and researchers with expertise in both archaeology and marine operations. The costs associated with mounting underwater archaeological expeditions can be prohibitive, especially for sites located in remote areas or at significant depths. This means that many underwater sites that might provide crucial evidence for understanding ancient civilizations remain unexplored, leaving room for speculation and alternative interpretations to flourish in the absence of definitive archaeological data. The waters around Japan contain numerous other underwater features and archaeological sites that have received less attention than the Yonaguni Monument, but that also provide valuable evidence for understanding the region's prehistoric and historic past. The Japanese archipelago has experienced significant tectonic activity throughout its geological history, including earthquakes, volcanic eruptions, and episodes of subsidence and uplift that have dramatically altered coastlines and created complex underwater landscapes. Some terrestrial archaeological sites have been submerged by tectonic subsidence, while rising sea levels in the aftermath of the last ice age have inundated coastal areas that were once inhabited. Japanese maritime archaeologists have documented numerous shipwrecks spanning several centuries of seafaring history, from medieval trading vessels to warships from the feudal period. These wrecks provide valuable information about shipbuilding technology, maritime trade routes, and the material culture of various historical periods. The study of submerged landscapes and prehistoric archaeology in Japan has also revealed evidence of human occupation dating back to the Paleolithic period, when the Japanese islands were connected to the Asian mainland by land bridges that are now submerged beneath the Sea of Japan and the East China Sea. During periods of maximum glaciation, when sea levels were more than 100 meters lower than they are today, it would have been possible to walk from the Asian continent to the Japanese archipelago across what is now open water. Archaeological sites from this period are rare in Japan because many of them would have been located in coastal lowlands that are now underwater, but those that have been discovered on land provide tantalizing glimpses of the lifeways and cultural practices of the earliest inhabitants of the Japanese islands. Understanding the full extent of human occupation during these early periods will likely require extensive underwater archaeological survey and excavation of the now submerged coastal plains and river valleys. Returning to the broader question of lost civilizations and the archaeological evidence for advanced prehistoric cultures, it is important to consider the site discovered in the Gulf of Khambhat, also known as the Gulf of Khambhat, off the western coast of India. This site, which was first reported in the early 2000s based on sonar surveys and subsequent diving investigations, consists of what appear to be structural remains including foundations, walls, and other architectural features located at depths of approximately 30 to 40 meters. The discoverers of the site reported recovering artifacts including pottery, beads, and pieces of worked wood that were subsequently subjected to radiocarbon dating. Some of these dates suggested ages of more than 9,000 years, which if accurate would make this one of the oldest urban settlements ever discovered and would predate the well-known Indus Valley civilization by several millennia. The announcement of the Gulf of Khambhat discovery generated considerable excitement and controversy within the archaeological community. If the site truly represented a 9,000-year-old city, it would require significant revision of our understanding of the development of civilization in South Asia and would push back the origins of urbanism, monumental architecture, and complex social organization by thousands of years. The site would also support theories that have been proposed by some researchers suggesting that rising sea levels at the end of the last ice age may have inundated important centers of early civilization, particularly in coastal areas where environmental conditions would have been favorable for the development of agriculture and permanent settlements. The drowning of these hypothetical coastal civilizations might help explain certain discontinuities and puzzles in the archaeological record, such as the apparently sudden emergence of complex societies in various parts of the world without clear local antecedents. However, the Gulf of Khambhat site has also been subject to significant criticism and skepticism from many archaeologists who question both the interpretation of the sonar data and the reliability of the artifact dates. Sonar imaging of underwater features can be ambiguous and difficult to interpret, particularly in areas with complex bottom topography or significant sediment deposition. What appears on a sonar image to be a wall or foundation might in fact be a natural geological feature, a modern debris field, or a concentration of artifacts and materials deposited by currents rather than a coherent architectural structure. The turbid waters of the Gulf of Khambhat, which receives enormous volumes of sediment from rivers including the Nirmada, create challenging conditions for underwater visibility and make it difficult for divers to adequately assess and document features observed on sonar surveys. This has led some critics to suggest that the architectural interpretations of the sonar data are speculative and that more systematic underwater investigation would be necessary to confirm the presence of human structures. The radiocarbon dates obtained from artifacts recovered at the Gulf of Khambhat site have also been questioned on methodological grounds. Radiocarbon dating can be problematic in marine environments because of the reservoir effect, which can cause marine organisms and objects that have been in contact with seawater to appear older than they actually are. Additionally, wood and other organic materials can be transported by currents and deposited far from their original context, meaning that a radiocarbon date on a piece of wood found at an underwater site does not necessarily date the construction or use of structures at that location. Some critics have suggested that the dated materials from the Gulf of Khambhat may be out of context or may have been contaminated, leading to anomalously old ages that do not accurately reflect the age of human occupation at the site. They have called for more systematic excavation, better stratigraphic control, and additional dating of multiple samples before accepting the extraordinary chronological claims that have been made for the site. Despite these criticisms, the Gulf of Khambhat site remains an important reminder of how much we still have to learn about the prehistoric occupation of coastal areas and the impact of sea level rise on the preservation and accessibility of archaeological sites. The Indian subcontinent has one of the longest records of human occupation anywhere in the world, with evidence of hominin presence extending back hundreds of thousands of years, and a rich archaeological record documenting the development of various cultural traditions and technological innovations. The coastal areas of India would have been attractive to prehistoric populations because of the abundant marine resources, moderate climate, and access to both terrestrial and aquatic ecosystems. During periods of lower sea level, these coastal zones would have extended far beyond the current shoreline, creating extensive lowland areas that are now submerged. It is entirely plausible that significant archaeological sites exist in these submerged areas, and systematic underwater survey and excavation will undoubtedly yield important discoveries in the years to come. The question of lost civilizations and catastrophic sea level rise brings us to consider the mechanisms and timescales of climate change and how these have affected human populations throughout history. The transition from the last ice age to the current interglacial period known as the Holocene was not a smooth or gradual process, but was marked by episodes of rapid change including dramatic temperature fluctuations, shifts in precipitation patterns, and most significantly for our purposes, rapid pulses of sea level rise. These meltwater pulses, as they are known to climate scientists, occurred when large portions of the continental ice sheets became unstable and disintegrated, releasing vast quantities of freshwater into the oceans in geologically brief periods of time. The most significant of these events occurred approximately 14,000 years ago and again approximately 8,000 years ago, with smaller pulses occurring at various other times during the deglaciation process. The impact of these rapid sea level rises on human populations would have been catastrophic in coastal areas. Communities that had been established for generations or even centuries on what they perceived to be stable coastlines would have found themselves inundated by rising seas, forcing them to abandon their settlements and migrate inland or to higher ground. The rate of sea level rise during meltwater pulse events could be on the order of meters per century, fast enough that individuals would have perceived the changes within their own lifetimes, and fast enough that not all communities would have been able to successfully adapt. The archaeological evidence of these disrupted coastal communities is now largely underwater, preserved in sediments on the continental shelves, and is only beginning to be systematically investigated by underwater archaeologists using modern technology. The psychological and cultural impact of witnessing such dramatic environmental changes may have influenced the development of flood myths and deluge narratives that appear in the religious and cultural traditions of societies around the world. Stories of great floods that destroyed previous worlds or civilizations appear in Mesopotamian, Hebrew, Greek, Hindu, Chinese, and numerous indigenous American traditions, among others. While these myths differ in their details and theological interpretations, they share common themes of divine or natural forces causing catastrophic flooding that destroys most of humanity, with only a few survivors who go on to repopulate the earth. Some researchers have suggested that these flood myths may preserve folk memories of actual catastrophic sea level rise events that occurred during the end of the Ice Age, passed down through oral traditions over hundreds of generations before being written down in the historical period. This hypothesis is controversial and difficult to test rigorously, as the relationship between oral tradition and historical events is complex and mediated by countless retellings, cultural transformations, and literary elaborations over time. However, the fact that detailed environmental information can sometimes be preserved in oral traditions has been demonstrated through ethnographic studies of indigenous peoples in various parts of the world, some of whom maintain remarkably accurate knowledge of landscape changes, astronomical phenomena, and historical events that occurred centuries or even millennia in the past. The Aboriginal people of Australia, for example, have oral traditions describing the formation of various landscape features and the flooding of coastal areas that appear to accurately preserve information about events that occurred at the end of the last ice age, 10,000 or more years ago. If such information can be transmitted accurately over such time spans in non-literate societies, it is at least plausible that other cultures might have preserved memories of catastrophic flooding events in their mythological and religious narratives. The deep ocean, the vast realm of water beyond the continental shelves where the seafloor plunges to depths of thousands or even thousands of meters, represents a fundamentally different environment from the relatively shallow coastal waters where most underwater archaeology takes place. In these abyssal depths, the conditions are so extreme that they challenge our very concepts of habitability and life. The pressure at the bottom of the deepest ocean trenches exceeds 1,000 atmospheres, enough to crush most human-made vessels and equipment like tin cans. The temperature hovers just above freezing, maintained not by seasonal variation, but by the slow circulation of deep ocean currents that originate in polar regions. And perhaps most significantly, sunlight cannot penetrate to these depths, meaning that photosynthesis is impossible, and the entire ecosystem must operate on fundamentally different principles than those that govern life in the sunlit surface waters. For more than a century after the development of oceanography as a scientific discipline, the prevailing assumption was that the deep ocean floor was a biological desert, a realm of eternal darkness and crushing pressure where life, if it existed at all, would be sparse and primitive. This assumption seemed reasonable given what was known about the energy requirements of living organisms and the apparent absence of any energy source in the deep sea. The first hints that this assumption was incorrect came from deep-sea trawling expeditions in the late 19th and early 20th centuries, which recovered bizarre and often grotesque creatures from depths that had been thought uninhabitable. These organisms, which included strange fish with enormous jaws and bioluminescent organs, delicate gelatinous invertebrates, and enormous crustaceans, demonstrated that life had found ways to survive in even the most extreme environments on Earth. The true revolution in our understanding of deep-sea ecosystems came with the discovery of hydrothermal vents in the late 1970s. These remarkable features, which occur along mid-ocean ridges where tectonic plates are spreading apart and new oceanic crust is being formed, are essentially underwater hot springs where superheated water enriched with minerals and chemicals erupts from cracks in the seafloor. The water emerging from these vents can reach temperatures of several hundred degrees Celsius, hot enough to melt lead, though it does not boil because of the enormous pressure at these depths. When this hot, mineral-rich water meets the cold ocean water, the dissolved minerals precipitate out, creating chimney-like structures that can grow to heights of tens of meters. These hydrothermal vent systems host extraordinary biological communities that operate on chemosynthesis rather than photosynthesis, with bacteria at the base of the food chain that derive energy from the oxidation of hydrogen sulfide and other chemicals in the vent fluids rather than from sunlight. The organisms that inhabit hydrothermal vent communities are among the most alien life forms on Earth, so strange and specialized that their discovery forced biologists to radically reconsider what is possible in terms of biological adaptation and evolution. Giant tube worms lacking mouths or digestive systems derive their nutrition from symbiotic bacteria living in specialized organs within their bodies. Eyeless shrimp swarm in the superheated water near the vents, using specialized organs that can detect infrared radiation to avoid swimming into lethally hot water. Crabs, clams, and various other invertebrates crowd around the vents, all ultimately dependent on the chemosynthetic bacteria that form the foundation of these ecosystems. The discovery of these communities demonstrated that life does not require sunlight and can thrive in conditions that would have been considered impossible just a few decades ago. This realization has profound implications not just for our understanding of terrestrial biology, but also for astrobiology and the search for life on other worlds, as it suggests that life might exist in environments previously thought to be sterile, such as the ice-covered oceans of Europa or Enceladus. Beyond the spectacular hydrothermal vent communities, research has revealed that even the apparently barren abyssal plains, the vast flat expanses of soft sediment that cover much of the deep ocean floor, support diverse biological communities. These communities are adapted to conditions of extreme food scarcity, as the only energy available comes from the slow rain of organic particles falling from the surface waters far above, known as marine snow. The organisms that live in these sediments, including various worms, crustaceans, and other invertebrates, have evolved remarkable physiological and behavioral adaptations that allow them to survive on minimal food intake and in some cases to remain dormant for extended periods when food is entirely absent. The metabolic rates of these organisms are extraordinarily slow compared to their shallow water relatives, with some individuals potentially living for centuries and growing at rates so slow as to be almost imperceptible. The Mariana Trench, the deepest part of the world's oceans, located in the western Pacific Ocean east of the Philippines, represents the ultimate extreme environment on Earth. The bottom of the trench, known as the Challenger Deep, lies approximately 11,000 meters below sea level, deeper than Mount Everest is tall. The pressure at this depth exceeds 1,100 atmospheres, the temperature is barely above freezing, and the conditions would seem to preclude the existence of life. Yet expeditions to the bottom of the Challenger Deep, using specially designed submersibles and remotely operated vehicles, have documented the presence of various life forms including amphipods, sea cucumbers, and various species of fish, all adapted to survive in these most extreme conditions. The discovery of a fish, subsequently named the Mariana snailfish, living at depths exceeding 8,000 meters, demonstrated that vertebrate life is possible even at these crushing pressures. Though the fish has had to evolve numerous specializations including extremely flexible bones, special proteins that remain functional under high pressure, and a body structure that lacks the gas-filled swim bladder that most fish use for buoyancy control. One of the most intriguing aspects of life in the deep ocean is the phenomenon of deep-sea gigantism, the tendency for certain types of organisms to grow to much larger sizes than their shallow water relatives. Giant squid, which can reach lengths of more than 10 meters, are perhaps the most famous examples of this phenomenon, but it also occurs in isopods, amphipods, and various other invertebrate groups. The causes of deep-sea gigantism are not entirely understood, but several factors may contribute to the pattern. The cold temperatures of the deep ocean slow metabolic rates, potentially allowing organisms to live longer and therefore grow larger. The scarcity of food in deep-sea environments might select for larger body sizes, as larger animals can go longer without eating and are more efficient at capturing and processing rare prey items. The reduced predation pressure in the deep sea compared to shallow waters might also allow animals to grow larger without the risk of being eaten before they reach reproductive maturity. The deep ocean is also home to some of the most remarkable bioluminescent displays found anywhere in nature. In the darkness of the deep sea, where sunlight never penetrates, many organisms have evolved the ability to produce their own light through chemical reactions involving specialized proteins and enzymes. This bioluminescence serves various functions depending on the species and context. Some fish use bioluminescent lures to attract prey, dangling glowing appendages in front of their mouths to draw in curious smaller fish. Others use bioluminescence for communication, flashing patterns of light to attract mates or coordinate behavior with others of their species. Still others use bioluminescence for defense, either to startle predators or to create confusing displays that allow them to escape while the predator is disoriented. The diversity of bioluminescent systems and the variety of ways in which light production has been incorporated into the life strategies of deep-sea organisms provide a fascinating example of convergent evolution and the creative power of natural selection operating in extreme environments. Recent research has revealed that life in the deep ocean extends even deeper than the surface of the seafloor. Scientists studying the geology and geochemistry of oceanic crust have discovered that microorganisms inhabit the cracks and pore spaces within the basaltic rocks that form the ocean floor, living in what is known as the deep biosphere. These microorganisms, primarily bacteria and archaea, survive not by photosynthesis or even chemosynthesis based on chemicals from hydrothermal vents, but through metabolic pathways that extract energy from reactions between rocks and water. As seawater circulates through cracks in the oceanic crust, it reacts with minerals in the basalt, producing hydrogen gas and other reduced compounds that can be used by microorganisms as energy sources. These deep biosphere communities are completely independent of the surface world and could in principle survive even if all life on the surface were extinguished. The discovery of this deep biosphere has profound implications for our understanding of the total amount of life on Earth and the diversity of environments where life can exist. Scientists estimate that the biomass of microorganisms living within the oceanic crust may rival or even exceed the biomass of all life in the oceans above, suggesting that we have only begun to understand the full extent and diversity of the terrestrial biosphere. These deep subsurface organisms live at incredibly slow metabolic rates, with individual cells potentially dividing only once every 1,000 years or even longer. They exist in a realm where the flow of time seems to operate on fundamentally different scales than those we experience in the surface world, where seasons and days provide regular rhythms to life. The study of the deep biosphere has also raised important questions about the origin of life on Earth and the possibility that life might have originated not in shallow tide pools or surface waters, as traditionally assumed, but in deep subsurface environments where conditions were more stable and protected from the bombardment and environmental catastrophes that affected the early Earth's surface. Some researchers have proposed that the earliest forms of life might have been chemolithic autotrophs, organisms that derive energy from reactions between rocks and water, and that build their cellular structures from inorganic carbon sources, similar to the microorganisms found in the deep biosphere today. If this hypothesis is correct, then the familiar surface ecosystems based on photosynthesis might represent a later evolutionary innovation rather than the original form of life on Earth. As we probe deeper into the ocean and discover more about the extraordinary diversity of life in extreme environments, we are also forced to confront the vulnerability of these ecosystems to human impacts. The deep ocean, despite its remoteness and apparent isolation from human activities, is not immune to the effects of pollution, climate change, and resource extraction. Plastic debris has been found in the deepest parts of the ocean, carried down by currents and sinking particles. Chemical pollutants, including heavy metals and persistent organic compounds, accumulate in deep-sea sediments and in the tissues of deep-sea organisms. Rising ocean temperatures and changing chemistry associated with increasing atmospheric carbon dioxide are altering deep-sea ecosystems in ways that are only beginning to be understood. And the expansion of deep-sea mining, fishing, and other extractive industries threatens to damage or destroy fragile ecosystems before we have even had the chance to study and understand them. The protection and conservation of deep-sea ecosystems present unique challenges because these environments are located in international waters beyond the jurisdiction of any single nation, and because the economic pressures to exploit deep-sea resources are substantial. Deep-sea mining companies are interested in harvesting manganese nodules, polymetallic crusts, and hydrothermal vent deposits that contain valuable minerals including copper, nickel, cobalt, and rare earth elements. These resources are increasingly important for manufacturing batteries, electronics, and other technologies essential to modern industrial society. And as terrestrial sources become depleted or more difficult to access, the economic incentive to mine the deep sea will only increase. However, the environmental impact of deep-sea mining is likely to be severe and long-lasting, potentially destroying unique ecosystems and species before they have even been scientifically described. The slow growth rates and low reproductive rates of many deep-sea organisms mean that recovery from disturbance, if it is possible at all, will take centuries or millennia. International efforts to establish regulatory frameworks for deep-sea resource management are ongoing, but face significant political and economic obstacles. The International Seabed Authority, established under the United Nations Convention on the Law of the Sea, is responsible for regulating mining activities in international waters, but its effectiveness is limited by competing national interests and the difficulty of enforcing regulations in remote areas where monitoring and oversight are technically challenging and expensive. Environmental organizations and scientists have called for the establishment of marine protected areas in the deep ocean and for moratoria on deep-sea mining until the environmental impacts can be better understood and appropriate safeguards put in place. However, these calls must compete with powerful economic interests and with the argument that deep-sea resources are necessary for the transition to renewable energy and other environmental goals. The deep ocean also holds secrets relevant to understanding Earth's climate system and how it has changed over geological time. The sediments that accumulate on the ocean floor preserve a detailed record of environmental conditions extending back millions of years, with each layer of sediment representing a snapshot of ocean chemistry, water temperature, biological productivity, and other parameters that can be reconstructed through careful analysis of fossils, chemical signatures, and physical properties of the sediments. By drilling cores from the ocean floor and analyzing them in detail, scientists have reconstructed the history of Earth's climate, documenting the regular cycles of ice ages and interglacial periods driven by variations in Earth's orbit and orientation, as well as longer-term trends associated with plate tectonics, mountain building, and the evolution of life. This paleoceanographic record has been essential for understanding the natural range of climate variability and for putting contemporary climate change in proper geological context. One of the most significant findings from deep-sea sediment studies is the discovery that Earth's climate can change rapidly and dramatically in response to relatively small perturbations in the climate system. The sediment record documents numerous instances of abrupt climate change, including sudden warming and cooling events, rapid shifts in ocean circulation patterns, and dramatic changes in biological productivity. These events demonstrate that the climate system has tipping points, thresholds beyond which feedbacks can amplify initial changes and drive the system into new states. Understanding these tipping points and the mechanisms that control them is crucial for predicting how Earth's climate will respond to ongoing increases in greenhouse gas concentrations and for assessing the risks associated with different levels of warming. The ocean also plays a critical role in regulating Earth's climate through its capacity to absorb heat and carbon dioxide from the atmosphere. The ocean has absorbed approximately 90% of the excess heat trapped by increasing greenhouse gas concentrations over the past several decades, moderating the rate of atmospheric warming, but also leading to thermal expansion of seawater and contributing to sea level rise. The ocean has also absorbed approximately 1/4 of the carbon dioxide emitted by human activities, reducing the rate at which atmospheric carbon dioxide concentrations are increasing, but also causing ocean acidification, a change in the chemistry of seawater that affects the ability of marine organisms to build shells and skeletons from calcium carbonate. These services that the ocean provides to the climate system come at a cost to marine ecosystems, and understanding these trade-offs is essential for managing human impacts on the ocean and for predicting how the ocean will respond to future climate change. As we explore the deep ocean and uncover its secrets, we are reminded of how much remains unknown about our own planet and how much we still have to discover about the diversity and resilience of life. The ocean covers more than 70% of Earth's surface, but remains one of the least explored and least understood environments on the planet. We have better maps of the surface of Mars than we have of most of the ocean floor. We have sent humans to the moon, but have sent them to the deepest parts of the ocean only a handful of times. This disparity in exploration effort reflects both the technical difficulties of exploring the ocean and the cultural and political priorities that have historically favored space exploration over ocean exploration. However, there are signs that this is beginning to change as new technologies make ocean exploration more feasible, and as the importance of the ocean for climate regulation, resource provision, and biodiversity becomes more widely recognized. Advanced technologies including autonomous underwater vehicles, remotely operated vehicles, sophisticated sonar mapping systems, and improved materials for constructing pressure-resistant equipment are enabling scientists to explore the ocean with unprecedented detail and efficiency. These technologies allow researchers to conduct systematic surveys of large areas of the seafloor, to investigate features at high resolution, and to collect samples from environments that were previously inaccessible. The data generated by these investigations are revealing an ocean floor that is far more geologically and biologically diverse than previously imagined, with seamounts, ridges, canyons, and other topographic features creating a complex mosaic of habitats that support distinct biological communities. One of the most intriguing recent discoveries in deep-sea biology involves the mysterious circular depressions and patterns found on abyssal plains in various parts of the world ocean. These features, which can range from a few centimeters to several meters in diameter and which are often arranged in regular geometric patterns, puzzled scientists when they were first documented in underwater photographs and videos. Various hypotheses were proposed to explain these enigmatic structures, including feeding traces of unknown organisms, artifacts of geological processes, or even evidence of underwater springs or vents. The mystery was solved through patient observation using time-lapse cameras and remotely operated vehicles, which revealed that at least some of these patterns are created by the feeding behavior of the Dumbo octopus, a group of deep-sea octopuses named for the ear-like fins they use for swimming, which give them a superficial resemblance to the cartoon character. The Dumbo octopus creates these patterns through a feeding strategy that involves hovering above the seafloor and using its arms to probe the sediment for small invertebrates and other prey items. As the octopus moves across the seafloor in search of food, it leaves behind a characteristic pattern of depressions where it has disturbed the sediment. The regular spacing and geometric arrangement of some of these patterns suggest that the octopuses are following systematic search patterns to maximize their feeding efficiency, behavior that demonstrates a level of spatial awareness and behavioral complexity not previously appreciated in deep-sea invertebrates. This discovery illustrates how even apparently simple observations of seafloor features can reveal important insights into the behavior and ecology of deep-sea organisms when combined with patient observation and careful analysis. The Dumbo octopus itself is a remarkable example of adaptation to deep-sea life. Unlike their shallow water relatives that propel themselves primarily by jet propulsion, Dumbo octopuses have evolved large fin-like structures that allow them to swim more efficiently in the energy-poor deep-sea environment where conserving energy is crucial. They are soft-bodied and gelatinous, adaptations that reduce their metabolic demands and allow them to cope with the extreme pressure of the deep sea. They have relatively large eyes compared to other deep-sea organisms, suggesting that they rely on vision despite the darkness of their environment, possibly using bioluminescence produced by other organisms as their source of light. The various species of Dumbo octopuses are found at depths ranging from several hundred to more than 7,000 meters, making them among the deepest living octopuses known to science. The study of deep-sea octopuses and their relatives has revealed remarkable diversity in this group of mollusks, with new species continuing to be discovered regularly as exploration of deep-sea environments expands. Some species have evolved unusual reproductive strategies adapted to the challenges of finding mates in the vast darkness of the deep ocean, including the retention of eggs in special pouches until they are ready to hatch, unlike most octopuses that attach their eggs to rocks or other substrates and guard them until hatching. Others have evolved specialized feeding adaptations that allow them to exploit particular food resources, such as the ability to bore through the shells of deep-sea snails or to capture gelatinous prey items that other predators cannot handle. The evolutionary relationships among deep-sea octopuses and their shallow water relatives are still being worked out using a combination of morphological and molecular data, but it is clear that the invasion of deep-sea habitats has occurred multiple times independently in octopus evolution, suggesting that this lifestyle offers significant advantages despite its obvious challenges. The broader group of cephalopods, which includes octopuses, squids, cuttlefish, and the chambered nautilus, represents one of the most remarkable success stories in the history of life, with members of this group having adapted to virtually every marine environment from shallow tide pools to the deepest ocean trenches. The cephalopods are mollusks, relatives of snails and clams, but they have evolved a body plan and lifestyle that is radically different from other mollusks and that in some ways parallels that of vertebrates. They have large, complex brains, sophisticated sensory systems including camera-type eyes that rival those of fish and mammals in their optical quality, and behavioral repertoires that include learning, problem-solving, and in some species what appears to be play behavior. The intelligence of cephalopods, particularly octopuses, has been the subject of intensive study and considerable debate, with some researchers arguing that these animals represent an independent evolutionary experiment in the development of complex cognition, a fundamentally different solution to the problems of survival and reproduction than the one that led to human intelligence. The evolution of complex nervous systems and sophisticated behavior in cephalopods is particularly intriguing because it occurred along a completely different evolutionary lineage than vertebrate intelligence, meaning that any similarities in cognitive abilities must be the result of convergent evolution rather than inheritance from a common ancestor. The last common ancestor of cephalopods and vertebrates was a simple worm-like organism that lived more than 500 million years ago and that possessed only the most rudimentary nervous system. Everything about the structure and organization of cephalopod and vertebrate brains is different, from the types of neurons they contain to the way information is processed and stored. Yet both groups have evolved the ability to learn from experience, to recognize individuals, to solve novel problems, and to modify their behavior in complex ways based on environmental feedback. This convergence suggests that there may be fundamental principles governing the evolution of intelligence, constraints or attractors that shape how complex cognitive systems develop regardless of the specific biological substrate. The study of cephalopod cognition has also raised important ethical questions about how we treat these animals, particularly in the context of scientific research and aquaculture. If octopuses and their relatives possess significant cognitive abilities, and possibly some form of subjective experience, then we may have moral obligations to consider their welfare in ways that we do not for organisms with simpler nervous systems. Some countries and jurisdictions have begun to include cephalopods in animal welfare regulations that were originally designed primarily for vertebrates, recognizing that cognitive complexity rather than phylogenetic relationship should be the basis for ethical consideration. These developments reflect broader trends in scientific and ethical thinking about animal minds and the expanding circle of moral consideration as we learn more about the cognitive and emotional lives of non-human animals. Returning to the question of underwater archaeological discoveries and what they can tell us about human history, we must consider the broader implications of the sites and findings we have discussed. The underwater realm preserves a record of human activity and environmental change that is complementary to, but in some ways more complete than the terrestrial archaeological record. Sites that were abandoned or destroyed on land often leave only fragmentary remains that have been scattered, buried, or recycled by subsequent human activity or natural processes. Underwater sites, particularly those in deeper water or those that were rapidly buried by sediment, can preserve organic materials, structural details, and spatial relationships that provide uniquely detailed snapshots of particular moments in time. The trade-off is that underwater sites are more difficult and expensive to investigate and often require specialized expertise and equipment that are not readily available to most archaeological research projects. The future of underwater archaeology will likely be shaped by continued technological development that makes it possible to survey, map, and excavate underwater sites with increasing efficiency and decreasing cost. Autonomous underwater vehicles equipped with high-resolution sonar, cameras, and other sensors are already being used to conduct systematic surveys of large areas of seafloor, identifying potential archaeological sites that can then be investigated in more detail by human divers or remotely operated vehicles. Photogrammetric techniques that allow the creation of detailed three-dimensional models from overlapping photographs are making it possible to document underwater sites with a level of precision that rivals or exceeds what can be achieved through traditional archaeological drawing and mapping. And improvements in diving technology, including closed-circuit rebreathers and advanced mixed gas systems, are extending the depth and duration of dives that human archaeologists can safely conduct, opening up sites that were previously accessible only to remotely operated vehicles. As we conclude this first part of our exploration of underwater mysteries and discoveries, we are left with a profound appreciation for the complexity and diversity of the hidden world beneath the waves. From ancient hunting grounds preserved beneath the waters of Lake Huron to Bronze Age cities standing silent on the Mediterranean seafloor, from controversial megalithic monuments that challenge our understanding of prehistoric capabilities to the extraordinary ecosystems of the deep ocean that operate on principles fundamentally different from those in the sunlit surface world, the underwater realm continues to surprise, challenge, and inspire us. The ocean holds secrets that span the full range of human history and extend back into geological deep time, recording environmental changes, biological evolution, and the endless creativity of life adapting to every conceivable environment. As we develop new technologies and new approaches to exploring this vast frontier, we can be certain that many more discoveries await, each one adding new chapters to the story of our planet and our species. The mysteries that lie beneath the ocean's surface extend far beyond the archaeological sites and geological formations we have explored thus far. The underwater world encompasses a vast temporal range, from the most recent maritime disasters whose causes remain disputed and controversial, to geological processes that have been operating for millions of years, shaping the seafloor and creating conditions for life in the most unexpected places. As we continue our journey into the depths, we will examine how human tragedy intersects with political intrigue, how microscopic life forms inhabit environments that seem utterly hostile to biological processes, and how the deep ocean serves as both a repository of Earth's history and a laboratory for understanding the fundamental principles that govern life itself. The relationship between human civilization and the sea has always been complex and often tragic. For thousands of years, people have ventured onto the ocean in vessels of increasing size and sophistication, seeking new lands, pursuing trade and commerce, waging war, and simply traveling from one place to another. The sea has facilitated human expansion and cultural exchange, but it has also claimed countless lives through shipwrecks, storms, and maritime disasters. Each sunken vessel tells a story, not just of the moment of its destruction, but of the people who built it, sailed it, and ultimately perished with it or survived to tell the tale. Maritime archaeology, the study of ships, boats, and other watercraft, as well as the material culture associated with seafaring, has become an important subdiscipline within archaeology, one that provides unique insights into technological development, economic systems, warfare, and daily life across many different cultures and time periods. Among the most controversial and intensely debated maritime disasters of the modern era is the sinking of the MS Estonia, a cruise ferry that went down in the Baltic Sea in the early morning hours of September 28, 1994, while traveling from Tallinn, Estonia to Stockholm, Sweden. The disaster claimed 852 lives, making it one of the deadliest maritime disasters in European waters during peacetime. The official investigation concluded that the accident was caused by the failure of the bow visor, a large hinged door that covered the bow ramp through which vehicles entered and exited the ship. According to this explanation, the bow visor detached from the ship in heavy seas, allowing water to flood the car deck, which caused the vessel to list severely and eventually capsize. The rapidity with which the ship sank, less than 30 minutes from the first signs of trouble to final capsizing, meant that most passengers and crew had no time to reach lifeboats or even to don life jackets, and the cold water temperature of only 10 to 15 degrees Celsius meant that those who did make it into the water had only minutes to live unless they could reach a life raft or be rescued. However, this official explanation has been challenged by alternative theories and by evidence that has emerged in the years since the disaster, leading to accusations of a cover-up and conspiracy at the highest levels of government. Some researchers and journalists who have investigated the disaster have argued that the bow visor failure was not the primary cause of the sinking, but rather a consequence of a collision with another vessel, possibly a submarine, that created a hole in the hull below the waterline. They point to witness testimony from survivors who reported hearing a loud impact or explosion before the ship began to list, to sonar images of the wreck that some interpret as showing damage inconsistent with bow visor failure alone, and to various irregularities in the official investigation, including the destruction of evidence and the apparent intimidation of witnesses. These alternative theories have been fueled by the decision of the governments involved in the investigation to seal the wreck site and prohibit independent diving or research, ostensibly to respect the sanctity of the grave site, but viewed by skeptics as an attempt to prevent scrutiny of evidence that might contradict the official narrative. The controversy surrounding the MS Estonia has been intensified by geopolitical factors and by suggestions that the ship may have been carrying secret cargo at the time of its sinking. The disaster occurred during a period of significant political and military tension in the Baltic region, just a few years after the collapse of the Soviet Union, and during a time when the newly independent Baltic states were seeking to establish their sovereignty and align themselves with Western institutions. Some theories suggest that the Estonia may have been transporting military equipment, radioactive materials, or other sensitive cargo that was being smuggled out of the former Soviet Union, and that knowledge of this cargo and the desire to keep it secret motivated the decision to seal the wreck and restrict access. These theories are necessarily speculative given the lack of definitive evidence, but they have found a receptive audience among those who distrust official narratives and who believe that governments routinely conceal information from the public when it serves political or security interests. The legal and ethical issues surrounding access to shipwreck sites, particularly those that contain human remains, are complex and contentious. On one hand, shipwrecks are archaeological sites that can provide valuable historical and scientific information, and preventing researchers from studying them means that this information is lost or remains unknown. On the other hand, shipwrecks are also graves, final resting places for people who died often in terrifying and tragic circumstances, and their families and communities may feel that these sites should be left undisturbed out of respect for the dead. Balancing these competing interests requires careful consideration of cultural values, legal frameworks, and the specific circumstances of each case. In some jurisdictions, shipwrecks are automatically protected as archaeological sites and can be investigated only with appropriate permits and oversight. In others, the wishes of descendant communities or the families of victims are given priority, and sites may be declared off-limits to research or even to recreational diving. The MS Estonia case is particularly complex because the decision to seal the wreck was made on behalf of the victims and their families, but not all families agreed with this decision, and some have actively campaigned for the wreck to be raised or at least thoroughly investigated to determine definitively what caused the disaster. These families argue that they have a right to know what happened to their loved ones and that the sealing of the wreck prevents them from obtaining closure and justice. They point to precedents from other maritime disasters where extensive investigation and recovery efforts were undertaken, including the raising of entire vessels or major portions of them, to determine causes and to recover human remains for proper burial. The fact that such efforts were deemed impractical or inappropriate in the case of the Estonia has reinforced suspicions that there is something about the wreck that authorities do not want to be discovered. In recent years, new investigations have been conducted using remotely operated vehicles equipped with cameras and sonar to document the wreck without disturbing it, and these investigations have revealed additional damage to the hull that some experts argue is inconsistent with the bow visor failure scenario. Specifically, there appears to be a large hole or rupture in the starboard side of the hull that could have been caused by a collision or possibly by an explosion. The debate over how to interpret this damage and what it means for understanding the cause of the disaster continues, with different experts reaching different conclusions based on the same evidence. This situation illustrates the challenges inherent in investigating maritime disasters, particularly when the wreck is in deep water, when access is restricted, and when political sensitivities and conspiracy theories complicate the interpretation of evidence. The MS Estonia disaster and the controversies surrounding it also raise broader questions about transparency, accountability, and public trust in official investigations of major accidents and disasters. When governments and authorities restrict access to evidence and decline to release information that might be relevant to understanding what happened, they create conditions in which alternative theories and conspiracy narratives can flourish, regardless of whether such theories are actually supported by evidence. The solution to this problem is not necessarily to make all information immediately public, as there may be legitimate reasons to protect certain details, particularly in cases involving national security or where release of information could cause unnecessary distress to victims' families. However, transparency about the reasons for restricting information, independent oversight of investigations, and mechanisms for revisiting conclusions when new evidence emerges can help to maintain public confidence in official findings, even when those findings are contested or unpopular. Moving from the realm of human tragedy to the domain of natural processes and biological discovery, we return to the deep ocean and the remarkable ecosystems that exist beneath the seafloor itself. The concept of a deep biosphere, a realm of microbial life inhabiting the pores and fractures of rocks hundreds or even thousands of meters beneath the surface, whether on land or under the sea, has revolutionized our understanding of the distribution and total biomass of life on Earth. For most of the history of biology as a scientific discipline, life was thought to be confined to a relatively thin veneer at the Earth's surface, extending from the upper atmosphere where microorganisms can be carried by winds, through the terrestrial and aquatic ecosystems we can directly observe, down to perhaps a few meters depth in soils and sediments where burrowing organisms and plant roots penetrate. The idea that life might exist at great depth within the Earth's crust was considered unlikely or impossible because of the extreme conditions, including high temperatures, high pressures, lack of oxygen, and apparent absence of energy sources that could sustain metabolism. The discovery of the deep biosphere began with drilling projects designed to study the geology and geochemistry of the Earth's crust, particularly the oceanic crust that forms the floor of the world's ocean basins. When scientists analyzed samples retrieved from these drilling projects, they were surprised to find that the rocks contained not just traces of organic material, which might have been contaminants introduced during the drilling process, but living microorganisms that were actively metabolizing and reproducing. These organisms were not simply dormant spores or dead cells preserved in the rock, but viable populations of bacteria and archaea that had adapted to survive in this extreme subsurface environment. Subsequent research has confirmed that these deep subsurface microorganisms are widespread, occurring in both oceanic and continental crust, and that they represent a significant fraction of the total microbial biomass on Earth, potentially equaling or exceeding the biomass of all microorganisms living in soils, oceans, and other surface environments. The microorganisms that inhabit the deep biosphere beneath the ocean floor face challenges that are fundamentally different from those encountered by their surface-dwelling relatives. They must obtain energy without access to sunlight, and often without access to the organic compounds produced by photosynthetic organisms at the surface. They must survive in environments where the temperature can approach or even exceed the boiling point of water, where the pressure is enormous, and where the availability of nutrients is extremely limited. They must cope with radiation from radioactive elements in the rocks, with toxic metals and chemicals, and with isolation from other organisms that might be potential sources of genetic exchange or metabolic cooperation. The fact that life not only exists but thrives under these conditions demonstrates the extraordinary adaptability and resilience of microbial life and forces us to expand our conception of what environments are habitable. The energy sources that sustain the deep biosphere are fundamentally different from those that power surface ecosystems. In the absence of sunlight and organic matter raining down from above, these microorganisms rely on chemolithotrophy, a metabolic strategy that involves extracting energy from chemical reactions between rocks and water. When seawater circulates through fractures in the oceanic crust, it reacts with minerals in the basaltic rock, particularly with iron-bearing minerals, producing hydrogen gas as a byproduct. This hydrogen can then be used by microorganisms as an electron donor in metabolic reactions, with various electron acceptors including sulfate, carbon dioxide, and oxidized iron compounds being reduced in the process. These reactions yield relatively small amounts of energy compared to photosynthesis or the metabolism of organic compounds, which means that the organisms must be extremely efficient in their energy use and must grow very slowly to survive on the meager energy available. The metabolic rates of deep biosphere microorganisms are indeed extraordinarily slow compared to those of surface-dwelling organisms. Measurements of metabolic activity in subsurface samples suggest that individual cells may divide only once every 100 years or even once every 1,000 years, generation times that are orders of magnitude longer than those of typical bacteria growing in nutrient-rich laboratory media, which can divide every 20 minutes to a few hours. These slow growth rates mean that populations turn over very slowly and that evolutionary change proceeds at a glacial pace. It also means that these organisms must have evolved mechanisms to maintain cellular integrity and repair damage over very long timescales, as a cell that takes 100 years to divide must be able to maintain its DNA, proteins, and other cellular structures in functional condition throughout that entire period despite ongoing damage from radiation, chemical reactions, and the inherent instability of biological molecules. The deep biosphere is not uniformly distributed throughout the oceanic crust, but is concentrated in particular regions and geological settings where conditions are most favorable for microbial life. The highest cell densities and metabolic activities are typically found in regions where hydrothermal circulation is active, where crustal fluids enriched in hydrogen and other reduced compounds are mixing with oxidized seawater, creating chemical gradients that can be exploited by microorganisms. These regions include the flanks of mid-ocean ridges where young oceanic crust is still warm and hydrothermally active, seamounts where fluid flow is focused by topography, and regions where oceanic crust is being subducted beneath continental margins and is being squeezed and dewatered by tectonic forces. In these settings, the combination of temperature, chemistry, and permeability creates conditions that are optimal for supporting microbial populations. One of the most significant findings from research on the oceanic deep biosphere is that the composition of microbial communities changes with depth and with the age of the oceanic crust. Near the seafloor, where temperatures are relatively cool and where there is greater connectivity to the overlying ocean, microbial communities include many organisms related to those found in marine sediments and in hydrothermal vent systems. These organisms include sulfate-reducing bacteria, methanogens, and various other groups that are well known from studies of surface and near-surface environments. Deeper in the crust, where temperatures are higher and where isolation from the surface is more complete, the microbial communities become dominated by thermophiles and hyperthermophiles, organisms adapted to growth at high temperatures, and by lineages that appear to be unique to the deep biosphere and that have no close relatives in surface environments. These endemic deep biosphere lineages may represent ancient evolutionary branches that have persisted in subsurface environments for hundreds of millions of years, isolated from the surface world and evolving independently. The discovery of these unique microbial lineages in the deep biosphere has important implications for understanding the tree of life and the evolutionary history of microorganisms. Traditional approaches to reconstructing microbial evolution have relied primarily on organisms that can be cultured in the laboratory or that can be detected in surface environments using molecular techniques. However, these approaches necessarily miss lineages that are restricted to environments that are difficult to sample or that cannot be cultured using standard methods. The deep biosphere represents one such environment, and the discovery of novel microbial lineages in subsurface samples suggests that there may be entire branches of the tree of life that we have only begun to explore. Characterizing these lineages and understanding their metabolic capabilities, evolutionary histories, and ecological roles is an ongoing challenge that requires combining cultivation-independent molecular techniques with creative approaches to simulating subsurface conditions in the laboratory. The study of the deep biosphere also has important implications for astrobiology and the search for life beyond Earth. If life can survive and even thrive in the extreme conditions of the deep subsurface on Earth, then similar life might exist in the subsurfaces of other planetary bodies where surface conditions are hostile, but where liquid water and energy sources might be available at depth. Mars, for example, has a cold and dry surface that is bathed in intense ultraviolet radiation, and that appears to be devoid of life. But beneath this inhospitable surface, there may be regions where liquid water exists in fractures and pore spaces in the crust, where reduced minerals and potential energy sources are available, and where microbial life similar to Earth's deep biosphere organisms might be able to survive. Similarly, the ice-covered ocean moons of the outer solar system, including Europa, Enceladus, and potentially others, have subsurface oceans that are isolated from direct sunlight, but that may have hydrothermal activity at their ocean floors, creating conditions similar to those at Earth's hydrothermal vents or in the deep biosphere. The discovery of life in such environments, if it could be confirmed, would provide powerful evidence that life is not unique to Earth, and that the basic biochemical and metabolic principles that underlie terrestrial life may be universal. The exploration of the deep biosphere is technically challenging and requires sophisticated drilling equipment capable of penetrating hundreds or thousands of meters into hard rock, while maintaining sterility to prevent contamination of samples with surface microorganisms. The drilling process itself can introduce heat, pressure, and fluids that alter the conditions in the borehole and potentially kill or damage the indigenous microorganisms, making it difficult to obtain samples that accurately represent the in situ conditions. Researchers have developed various strategies to address these challenges, including the use of tracers to detect and quantify contamination, the development of specialized sampling tools that can retrieve intact rock cores with minimal disturbance, and the establishment of subsurface observatories where instruments can be installed in boreholes to monitor conditions and microbial activity over extended periods. These technological developments are enabling increasingly sophisticated studies of the deep biosphere and are revealing new details about the diversity, distribution, and activity of subsurface microorganisms. One particularly intriguing aspect of the deep biosphere is the question of how these microorganisms originally colonized the subsurface and how they are maintained over geological time. There are two main hypotheses. The first is that deep biosphere microorganisms are descendants of organisms that were buried with the rocks when they formed and that have persisted in place ever since, a scenario that would mean some deep biosphere populations could be millions or even hundreds of millions of years old. The second hypothesis is that the deep biosphere is continually being reseeded by microorganisms transported from the surface through circulation of fluids, meaning that deep biosphere populations are younger and more dynamic than they might appear. Evidence exists to support both scenarios in different geological settings, suggesting that both processes may be important. In young oceanic crust near mid-ocean ridges, where hydrothermal circulation is vigorous, there is likely to be significant exchange with surface-derived microorganisms. In older, cooler crust where fluid circulation has slowed or stopped, isolated populations may persist for very long periods with minimal input from the surface. The possibility that microbial populations could remain viable and metabolically active over geological timescales raises profound questions about the nature of life and the meaning of concepts like individual and generation that we typically apply to biological organisms. A microorganism that divides once every 1,000 years is in some sense operating on timescales that are more geological than biological, existing in a state that is intermediate between active life and dormancy. The molecular mechanisms that allow such organisms to maintain viability over such long periods are poorly understood, but likely involve highly efficient DNA repair systems, protective structures that shield cellular components from damage, and metabolic strategies that minimize the production of damaging byproducts. Understanding these mechanisms could have practical applications for biotechnology and medicine, as the ability to preserve biological materials or to slow aging processes is of obvious interest. The deep biosphere beneath the ocean floor is just one component of a broader and more complex system of fluid circulation, chemical exchange, and biological activity that operates within the oceanic crust. When seawater penetrates into the crust through fractures and porous zones, it is heated by contact with hot rock and undergoes chemical reactions that alter both the water and the rock. The heated water, being less dense than cold seawater, rises back toward the seafloor, either erupting at hydrothermal vents or percolating more diffusely through the crust. This hydrothermal circulation system transports enormous quantities of heat from the Earth's interior to the ocean, influences the chemistry of seawater by adding or removing various elements, and provides energy and nutrients that support both the deep biosphere and the ecosystems at hydrothermal vents. The total amount of seawater that circulates through the oceanic crust over geological time is sufficient to cycle the entire volume of the ocean through the crust every few 100,000 years, meaning that this process has a major influence on ocean chemistry and on global biogeochemical cycles. The chemical exchanges that occur during hydrothermal circulation have important consequences for the concentration of various elements in seawater and in crustal rocks. When seawater is heated in the subsurface, magnesium and sulfate are removed from the water and incorporated into altered minerals in the rock, while metals including iron, manganese, copper, and zinc are leached from the rock and carried into the water. When this hot, metal-rich fluid emerges at hydrothermal vents, the metals precipitate out as sulfide minerals, forming the chimneys and mounds that characterize vent fields and creating deposits of metallic ores on the seafloor. These hydrothermal ore deposits have been recognized as potential targets for deep-sea mining, as they can contain high concentrations of valuable metals. However, mining these deposits would likely destroy or severely damage the unique biological communities that inhabit hydrothermal vents, creating a direct conflict between resource extraction and conservation. The study of hydrothermal circulation and its effects on ocean chemistry has also provided insights into how the Earth's oceans may have formed and how their chemistry has evolved over geological time. In the early Earth, volcanic activity was much more intense than it is today, and hydrothermal circulation would have been correspondingly more vigorous. This intense hydrothermal activity would have added large amounts of metals and other elements to the early oceans, creating very different chemical conditions than those that exist today. Some researchers have proposed that life may have originated in hydrothermal settings, where the chemical energy available from reactions between hot fluids and seawater could have driven the synthesis of organic molecules and the assembly of the first self-replicating systems. While this hypothesis remains controversial and difficult to test, the discovery of diverse and productive ecosystems at modern hydrothermal vents demonstrates that these environments can certainly support life, even if they were not necessarily where life first originated. The interconnections between geological processes, chemical cycles, and biological systems in the deep ocean illustrate a fundamental principle of Earth science, which is that the planet operates as an integrated system in which physical, chemical, and biological processes are intimately linked and mutually influence one another. The rocks influence the chemistry of the ocean, which influences what organisms can live where, which in turn influences the chemistry of the rocks through biological weathering and biomineralization. Energy from the Earth's interior drives tectonic processes that create new seafloor and recycle old seafloor, which creates habitats for organisms and provides energy sources for chemosynthetic ecosystems. The ocean circulates through the crust, altering both the rocks and the water, and carrying microorganisms into subsurface environments where they establish persistent populations that may endure for geological ages. Understanding any one component of this system requires understanding its connections to the others, and the deep ocean serves as a natural laboratory where these connections can be studied and where the principles governing Earth system dynamics can be elucidated. As we extend our exploration to other features of the deep ocean floor, we encounter additional mysteries and phenomena that challenge our understanding and that reveal the complexity of submarine environments. The abyssal plains, vast flat expanses of sediment-covered seafloor that constitute the largest habitat on Earth by area, have their own distinctive ecology and their own peculiar features. Among the most enigmatic of these features are the various patterns and structures that appear on the seafloor and that have, in many cases, resisted easy explanation. We have already discussed the octagonal patterns created by Dumbo octopuses, but there are other patterns and features that have different origins and that reveal different aspects of deep-sea ecology and behavior. The Dumbo octopus, whose feeding behavior creates distinctive patterns on the abyssal seafloor, represents a remarkable example of adaptation to the deep-sea environment and of how careful observation can solve apparently mysterious phenomena. When these patterns were first documented in photographs and videos from the deep seafloor, they appeared as regular arrays of shallow depressions or disturbed areas, often arranged in geometric patterns that suggested some kind of organized or systematic process. Various hypotheses were proposed, including the possibility that the patterns represented feeding traces of unknown organisms, artifacts of sediment transport processes, or even burrow openings for animals living beneath the seafloor surface. The mystery was resolved through the deployment of time-lapse cameras and through direct observation using submersibles and remotely operated vehicles, which revealed that Dumbo octopuses were responsible for at least some of these patterns. The feeding strategy employed by Dumbo octopuses is known as benthic pelagic coupling, a term that refers to the interconnection between bottom-dwelling and water column processes and organisms. Dumbo octopuses are pelagic, meaning they swim in the water column rather than crawling on the seafloor like many other octopuses, but they feed primarily on benthic organisms, small invertebrates that live in or on the seafloor sediments. To feed, the octopus descends to just above the seafloor and uses its arms to probe the sediment, searching for prey by touch and possibly also by chemical cues. When it detects a prey item, the octopus uses its arms to extract it from the sediment and bring it to its mouth, leaving behind a small depression or disturbed area. The octopus then moves a short distance and repeats the process, gradually creating a line or pattern of feeding traces as it systematically searches an area of seafloor. The geometric regularity of some of these feeding trace patterns suggests that Dumbo octopuses employ systematic search strategies to maximize their feeding efficiency. Rather than searching randomly, which would result in the octopus repeatedly searching the same areas and missing others, the octopus appears to follow a regular spacing pattern that ensures thorough coverage of an area while minimizing wasted effort. This kind of optimal foraging behavior has been documented in many other animals, from bees collecting pollen to wolves hunting prey, and its presence in deep-sea octopuses suggests that these animals possess sophisticated cognitive abilities and spatial awareness. The ability to maintain a mental map of where one has already searched and to plan a search pattern that maximizes efficiency requires neural capabilities that go beyond simple stimulus response mechanisms, and that suggest a level of information processing previously unappreciated in deep-sea invertebrates. The various species of Dumbo octopuses, classified in the genus Grimpoteuthis and related genera, display remarkable diversity in body form, size, and ecology despite their superficial similarity in possessing the characteristic ear-like fins. Some species are relatively small, measuring only a few centimeters in length, while others can reach lengths of more than a meter. They vary in color from translucent to red to purple, though color is of limited significance in the darkness of the deep sea where most organisms cannot perceive it. The fins vary in size and shape, with some species having large prominent fins and others having smaller, less conspicuous ones. This diversity suggests that Dumbo octopuses have undergone an adaptive radiation in deep-sea environments, diversifying to exploit different ecological niches and resources. The reproductive biology of Dumbo octopuses is poorly known because of the difficulty of observing these animals in their natural habitat and the challenges of maintaining them in aquaria. However, what is known suggests some interesting adaptations to deep-sea life. Female Dumbo octopuses appear to be able to store sperm from males and to fertilize their eggs over an extended period, allowing them to reproduce even when encounters with males are infrequent. The eggs are relatively large and appear to be brooded or protected by the female in some species, though the details of parental care behavior are not well documented. The hatchlings emerge as miniature versions of the adults rather than going through a planktonic larval stage, an adaptation that may be advantageous in the deep sea, where currents could carry planktonic larvae far from suitable habitat. The study of Dumbo octopuses and other deep-sea cephalopods has been greatly facilitated by technological advances in deep-sea exploration, particularly the development of high-definition video cameras that can operate at great depths and that can capture detailed images of animals and their behavior. Earlier generations of deep-sea cameras produced grainy, low-resolution images that made it difficult to identify species or to discern behavioral details. Modern cameras can capture video in high definition and can often be equipped with lighting systems that provide illumination without disturbing the animals being observed. These technological improvements have revealed a wealth of previously unknown behaviors and interactions, and have demonstrated that the deep sea is far more dynamic and behaviorally complex than previously appreciated. The broader implications of discovering that deep-sea organisms engage in sophisticated behaviors and create recognizable patterns on the seafloor extend beyond the specific case of Dumbo octopuses. Each such discovery reminds us that the deep ocean is not the static, lifeless realm it was once imagined to be, but is instead a dynamic environment where organisms interact with their physical surroundings and with each other in complex ways. The patterns and features we observe on the seafloor are not merely geological artifacts, but are often the products of biological activity, traces of organisms going about their daily lives of finding food, avoiding predators, seeking mates, and creating shelter. Reading these traces and interpreting their meaning requires careful observation, comparative study, and often a good deal of patience and creativity, but the insights gained from such work contribute significantly to our understanding of deep-sea ecology and evolution. Another fascinating aspect of deep-sea biology that has emerged from recent research is the extent to which deep-sea organisms rely on fallen organic material from the surface ocean, a phenomenon known as food falls, or, in the case of large animal carcasses, whale falls. In the nutrient-poor environment of the deep seafloor, the arrival of a dead whale or other large animal represents a massive influx of food and energy, creating a temporary oasis of abundance that attracts a diverse assemblage of scavengers and specialist organisms. Researchers have documented the sequence of colonization and consumption that occurs at whale fall sites, revealing distinct stages characterized by different assemblages of organisms and different ecological processes. The initial stage of whale fall succession begins immediately when the carcass reaches the seafloor and is characterized by the arrival of mobile scavengers including hagfish, sleeper sharks, and various crustaceans that consume the soft tissues. These scavengers can strip a large whale carcass of most of its flesh within a matter of months, though the exact timing depends on the size of the carcass, the depth, and the temperature. The second stage, which can last several years, is characterized by the colonization of the bones and remaining tissues by specialist organisms, including various worms, crustaceans, and mollusks that bore into the bones, or that consume the lipid-rich oils contained within them. The third stage, which can persist for decades or even longer, is supported by chemosynthetic bacteria that derive energy from the decomposition of lipids in the bones, creating a chemical environment similar to that found at hydrothermal vents and supporting a community of organisms that includes many species also found at vents or other chemosynthetic habitats. The discovery of whale fall ecosystems has revealed that the deep seafloor is more heterogeneous and patchy than previously recognized, consisting not of a uniform expanse of sediment, but of a mosaic of different microhabitats including areas enriched by food falls, hydrothermal vents, cold seeps where methane or other hydrocarbons emerge from the seafloor, and background areas where food is scarce and organisms must survive on the meager rain of organic particles from above. These different habitats support different communities of organisms, and the connectivity among them, mediated by the dispersal of larvae and by the movement of mobile animals, influences the distribution and evolution of deep-sea biodiversity. Understanding this habitat heterogeneity and the processes that create and maintain it is essential for effective conservation and management of deep-sea ecosystems, particularly as human activities including fishing, mining, and waste disposal increasingly impact these remote environments. The concept of connectivity among deep-sea habitats and the role of rare events like whale falls in maintaining populations of specialist organisms has led to the development of what is known as the stepping stone hypothesis for deep-sea biodiversity. According to this hypothesis, organisms that are specialized for living at chemosynthetic habitats like vents and seeps, which are ephemeral and patchily distributed, can maintain regional populations by dispersing among these sites, using intermediate habitats like whale falls or other organic falls as stepping stones. When one vent site becomes inactive or one seep shuts down, the species that depended on it are not driven to extinction because they can colonize new sites as they become available, with populations at intervening whale falls or other falls serving as sources of larvae or as refugia during periods when suitable chemosynthetic habitats are unavailable. This hypothesis has been tested using genetic and phylogenetic analyses of vent and seep organisms, which have revealed that many species show evidence of genetic connectivity among widely separated sites, supporting the idea that dispersal and colonization are important processes shaping deep-sea biogeography. The study of deep-sea connectivity in biogeography has also revealed some surprising patterns, including the discovery that some deep-sea species have extraordinarily wide geographic ranges, occurring in all the world's ocean basins despite the apparent barriers to dispersal presented by ocean currents, temperature gradients, and the vast distances involved. These wide-ranging species are typically those with long-lived planktonic larvae that can be carried great distances by ocean currents, or those that are associated with highly mobile habitats like drifting wood or algal mats. Other species have very restricted ranges, occurring only at a single vent field or seep site or in a particular region of the ocean. Understanding what determines whether a species has a broad or restricted range is an important question in deep-sea ecology and has implications for how we assess extinction risk and prioritize conservation efforts. The deep ocean also serves as a repository for human-generated materials and pollutants, some intentionally disposed of and others accidentally lost or released. For decades, the ocean was used as a dumping ground for various types of waste, including industrial chemicals, radioactive materials, sewage, and munitions. The assumption was that the vastness of the ocean and the remoteness of the deep sea would render these materials harmless through dilution, and that they would remain isolated from human populations. We now know that this assumption was mistaken, and that pollutants can persist in the marine environment for extended periods, can accumulate in the tissues of marine organisms, and can be transported back to human populations through seafood consumption or through other pathways. The deep ocean is not isolated from the surface world, but is connected to it through the circulation of water, the migration of organisms, and the movement of particles, meaning that contaminants released anywhere in the ocean can eventually reach the deep sea. Among the most persistent and widespread pollutants found in the deep ocean are plastics, which have been documented in even the most remote and deepest parts of the ocean, including the Mariana Trench. These plastics range from large items like discarded fishing gear and bottles to microplastics, tiny fragments less than 5 millimeters in size that result from the breakdown of larger items or that are manufactured at small sizes for use in cosmetics and other products. Microplastics can be ingested by deep-sea organisms and can accumulate in their tissues, potentially causing physical harm or toxicity. The long-term effects of plastic pollution on deep-sea ecosystems are not yet well understood, but there is growing concern that these persistent materials could have significant impacts on deep-sea food webs and on the functioning of deep-sea ecosystems. Other pollutants found in the deep ocean include heavy metals from industrial activities and mining, persistent organic pollutants like PCBs and DDT that were manufactured for various purposes and that have since been banned or restricted but that remain in the environment, and radioactive contaminants from nuclear weapons testing, nuclear accidents, and the disposal of radioactive waste. These contaminants can accumulate in deep-sea sediments and in the tissues of deep-sea organisms, sometimes reaching concentrations that are higher than those found in surface waters, because of the tendency of certain pollutants to sink and accumulate in sediments or because of bioaccumulation through food chains. The presence of human-generated pollutants in the deepest parts of the ocean, far from any direct human activity, serves as a stark reminder of the global reach of human impacts and of the interconnectedness of Earth's systems. The study of pollution in the deep ocean is challenging because of the difficulty of obtaining representative samples from remote locations, and because of the need to distinguish between natural and anthropogenic sources of various elements and compounds. Some metals that are considered pollutants, like mercury and lead, also occur naturally in the environment and can be released through volcanic activity and weathering of rocks, so elevated concentrations do not necessarily indicate human impact. Determining the source of contaminants requires careful analysis of isotopic ratios, spatial patterns, and temporal trends, often combined with historical records of industrial activity, waste disposal, and atmospheric deposition. Despite these challenges, studies have clearly documented that human activities have altered the chemistry of the deep ocean, and that pollutants are now ubiquitous even in areas far from major population centers. The recognition that the deep ocean is vulnerable to human impacts has led to increased efforts to establish protected areas and to regulate activities that could harm deep-sea ecosystems. Marine protected areas which restrict or prohibit certain activities like fishing, mining, or waste disposal have been established in some deep-sea regions, though the total area protected remains a small fraction of the deep ocean. The effectiveness of deep-sea protected areas depends on adequate enforcement, which is challenging in remote areas far from land where monitoring and surveillance are difficult and expensive. It also depends on cooperation among nations, as much of the deep ocean lies in international waters beyond the jurisdiction of any single country, requiring multilateral agreements and coordinated management efforts. The regulatory framework for managing human activities in the deep ocean is complex and involves multiple international treaties and organizations. The United Nations Convention on the Law of the Sea provides a general framework for ocean governance, dividing the ocean into zones with different legal status and establishing principles for the management of marine resources and the protection of the marine environment. The International Seabed Authority, established under the Convention, is responsible for regulating mining activities on the deep seafloor in international waters, though it has not yet approved any commercial mining operations. Regional fisheries management organizations regulate fishing activities in various parts of the ocean, though their effectiveness varies and many deep-sea fish stocks have been depleted by overfishing. Various other international agreements address specific issues like pollution, endangered species, and the conservation of marine biodiversity, creating a complex patchwork of overlapping jurisdictions and responsibilities. One of the major challenges in ocean governance is the lack of comprehensive knowledge about deep-sea ecosystems and the impacts of human activities on them. Management decisions must often be made with incomplete information about species distributions, ecosystem functioning, and the resilience of populations to disturbance. This uncertainty argues for the application of the precautionary principle, which suggests that in the absence of complete scientific certainty, management decisions should err on the side of caution to prevent potentially irreversible harm. However, applying the precautionary principle in practice can be difficult because it requires balancing the potential for environmental harm against the economic and social benefits of activities like fishing and mining, and because different stakeholders may have very different assessments of risks and benefits. The future of the deep ocean will be shaped by the choices we make in the coming decades about how we manage human activities and how we balance exploitation of marine resources with conservation of marine ecosystems. The deep ocean provides valuable services to humanity, including climate regulation through the absorption of heat and carbon dioxide, the provision of seafood and other marine products, and the maintenance of biodiversity that may have value for medicine, biotechnology, and other applications. These services depend on the health and functioning of deep-sea ecosystems, which in turn depend on maintaining the physical, chemical, and biological processes that have operated in the ocean for millions of years. Understanding these processes, monitoring changes in ocean conditions, and developing sustainable approaches to ocean use are among the most important challenges facing marine science and ocean policy. As we contemplate the mysteries and wonders of the underwater world, we are inevitably drawn to reflect on the deeper questions about our place in nature and our responsibility to the planet that sustains us. The ocean, which covers most of Earth's surface and which contains the vast majority of the biosphere by volume, remains largely unknown to us despite centuries of exploration and study. Each voyage into the depths, each new discovery of a sunken city or a bizarre deep-sea creature or a previously unknown ecosystem reminds us of how much we have yet to learn and how much remains to be discovered. The underwater world challenges our assumptions, tests our technologies, and rewards our curiosity with revelations that expand our understanding of life, Earth, and perhaps ultimately ourselves. The archaeological sites submerged beneath the world's oceans and lakes preserve moments of human history frozen in time, offering glimpses of how our ancestors lived, what they valued, and how they responded to environmental changes that transformed their world. These sites remind us that coastlines are not permanent, that civilizations rise and fall, and that the Earth is a dynamic planet whose surface is constantly being reshaped by geological and climatic forces. The controversies surrounding sites like Yonaguni and the Gulf of Khambhat reflect deeper tensions in how we construct historical narratives and how we evaluate evidence that challenges established frameworks. While mainstream science demands rigorous proof before accepting extraordinary claims, the possibility that important sites remain undiscovered or unrecognized should keep us humble and open-minded about what we might yet find beneath the waves. The deep-sea ecosystems thriving in darkness and extreme pressure demonstrate that life is more versatile and more resilient than we might have imagined, capable of finding ways to survive and even flourish in conditions that seem utterly hostile. The discovery of chemosynthetic ecosystems, the deep biosphere, and the myriad of bizarre organisms adapted to life in the abyss has expanded our conception of habitability and has provided new perspectives on where and how life might exist beyond Earth. If microorganisms can survive in the fractured rocks beneath the seafloor, extracting energy from chemical reactions between water and minerals, might similar life exist in the subsurface of Mars or in the ice-covered oceans of Europa? The deep ocean serves as both a window into Earth's past and a laboratory for imagining life's possibilities elsewhere in the universe. The human stories intertwined with the ocean, from ancient mariners who ventured into unknown waters to the victims of maritime disasters like the MS Estonia, remind us of the ocean's power and its danger. The sea has been both highway and barrier throughout human history, enabling exploration and trade while also claiming countless lives. The controversies and mysteries surrounding shipwrecks and maritime disasters reflect our ongoing struggle to understand catastrophic events and to find meaning in tragedy. They also highlight the political and social dimensions of how we investigate and commemorate such events, and the tensions that can arise when official narratives are questioned or when evidence is restricted from public scrutiny. Looking forward, the greatest challenges facing the ocean are those created by human activities: overfishing, pollution, climate change, and the potential for destructive resource extraction. The choices we make in the coming years will determine whether the ocean's ecosystems can continue to function and provide the services upon which humanity depends, or whether we will degrade them beyond recovery. The deep ocean, long protected by its remoteness and inaccessibility, is becoming increasingly vulnerable as technology makes it possible to reach and exploit even the most remote regions. Balancing the human desire for resources and economic development with the need to preserve the ocean's health and biodiversity will require wisdom, foresight, and a willingness to prioritize long-term sustainability over short-term gain. The underwater world also offers inspiration and wonder, revealing beauty and complexity that can nourish the human spirit and that can remind us of our connection to the larger web of life. The bioluminescent displays of deep-sea creatures, the architectural precision of Bronze Age cities preserved beneath the waves, the intricate patterns created by an octopus searching for food on the abyssal plain, all of these phenomena speak to the diversity and creativity of nature and to the power of scientific inquiry to reveal hidden worlds. As we continue to explore the ocean and to uncover its secrets, we are not just accumulating knowledge for its own sake, but are also enriching our understanding of what it means to live on this remarkable planet. The technologies we have developed to explore the underwater world, submersibles that can dive to the deepest trenches, remotely operated vehicles that can work for extended periods on the seafloor, sonar systems that can map vast areas with precision, represent remarkable achievements of human ingenuity and determination. These tools have opened up a realm that was inaccessible to previous generations and have made it possible to study environments and organisms that were previously known only through fragmentary samples brought up in nets or dredges. As technology continues to advance, we can expect even more sophisticated capabilities, including autonomous vehicles that can explore the ocean for months or years without human intervention, sensors that can detect and identify organisms based on their DNA, and artificial intelligence systems that can process vast amounts of data to identify patterns and make discoveries that human researchers might miss. The intersection of archaeology, marine biology, geology, and other disciplines in the study of the underwater world demonstrates the power of interdisciplinary approaches to scientific questions. Understanding a submerged archaeological site requires expertise in both traditional archaeology and in marine geology, diving technology, and conservation science. Understanding a hydrothermal vent ecosystem requires knowledge of geology, chemistry, microbiology, and ecology. The most important discoveries and insights often come at the boundaries between disciplines, where different perspectives and methodologies can be combined to address questions that cannot be adequately tackled from within a single disciplinary framework. The underwater world, with its complexity and its challenges, provides an ideal arena for interdisciplinary collaboration and for the development of new approaches that transcend traditional academic boundaries. Education and public outreach are essential for ensuring that the discoveries made in the underwater world reach beyond the scientific community and inspire broader public interest and support for ocean exploration and conservation. Documentary films, museum exhibitions, popular books, and digital media can all play important roles in communicating the excitement of underwater discoveries and in fostering a sense of connection to the ocean. When people learn about the ancient cities beneath the Mediterranean, the bizarre creatures of the deep sea, or the microscopic life forms inhabiting fractured rocks beneath the seafloor, they often develop a greater appreciation for the ocean and a stronger commitment to protecting it. This public engagement can translate into political support for ocean research and conservation, as well as into individual actions that reduce impacts on marine ecosystems. The underwater world has captured human imagination for as long as people have looked out over the waves and wondered what lies beneath. Ancient myths and legends spoke of sea monsters and underwater kingdoms, of sunken cities and drowned lands. Modern exploration has revealed that while the specific details of these myths are fictional, the ocean truly does contain wonders that rival anything imagined by the ancients. Cities that have stood for thousands of years beneath the waves, creatures so strange they seem alien, and ecosystems operating on principles fundamentally different from those in the familiar surface world. The boundary between myth and reality, between imagination and discovery, has always been fluid in our relationship with the sea, and this continues to be true as we probe deeper into the ocean's secrets. As we conclude this exploration of the underwater world and its many mysteries, we are left with a profound sense of both accomplishment and humility. We have accomplished much in our quest to understand the ocean, developing technologies and methodologies that have revealed hidden worlds and answered questions that previous generations could only speculate about. Yet we remain humble in the face of how much we still do not know, how vast the ocean is, and how much remains to be discovered. Each answer we find seems to raise new questions. Each mystery solved reveals new mysteries waiting to be explored. This is the nature of scientific inquiry, the endless frontier of human curiosity and the persistent quest to understand the world around us. The underwater world teaches us that Earth is still a planet of discovery, that frontiers still exist not just in the distant reaches of space but here on our own world, beneath the waves that cover most of its surface. It teaches us that the familiar categories and assumptions we bring to our understanding of nature are often inadequate, that life is more diverse and adaptable than we imagine, and that the processes shaping our planet operate on timescales and spatial scales that challenge human comprehension. It teaches us humility in the face of natural complexity, respect for the resilience and fragility of ecosystems, and appreciation for the interconnectedness of all things. The future of underwater exploration will be shaped by the technologies we develop, the questions we choose to pursue, and the values we bring to our engagement with the ocean. Will we approach the ocean primarily as a resource to be exploited, or as a realm to be understood and protected? Will we learn from the past mistakes of overfishing and pollution, or will we repeat those mistakes in new contexts like deep-sea mining? Will we invest in the long-term research and monitoring needed to understand how the ocean is changing and how we can mitigate human impacts? These are not just scientific or technical questions, but ethical and political ones that will require wisdom and foresight to answer appropriately. The stories contained in the underwater world of ancient civilizations whose remains now rest beneath the waves, of maritime disasters that claimed hundreds of lives, of bizarre organisms thriving in conditions we would have thought impossible, of microscopic life forms inhabiting fractured rocks deep beneath the seafloor, are ultimately human stories as well as natural ones. They are stories about curiosity and discovery, about tragedy and resilience, about the relationship between humanity and the natural world. They remind us that we are part of nature, dependent on natural systems for our survival and well-being, and that our fate is intertwined with that of the ocean and all the life it contains. As we stand at the shore looking out over the waves, we can reflect on the vast realm that lies beneath, the ancient cities and hunting grounds, the towering mountains and deep trenches, the volcanic vents and abyssal plains, the countless organisms going about their lives in darkness and cold and crushing pressure. We can reflect on the generations of explorers and scientists who have ventured into this realm, and who have brought back stories and specimens and data that have transformed our understanding. And we can commit ourselves to continuing this exploration, to protecting what we find, and to passing on to future generations an ocean that is healthy, diverse, and full of wonder. The ocean's depths hold not just the secrets of the past, but also the keys to the future. Understanding how marine ecosystems function, how they respond to environmental change, and how they provide services essential to human welfare will be crucial for addressing the environmental challenges of the coming decades. The ocean plays a central role in regulating Earth's climate, providing food and resources to billions of people, and maintaining the biogeochemical cycles that make our planet habitable. Protecting the ocean and ensuring its health is not just an environmental imperative but a practical necessity for human survival and prosperity. The underwater world calls to us still, inviting exploration, promising discovery, and demanding respect. As we develop ever more sophisticated tools to explore the depths, as we uncover more of the ocean's secrets, and as we come to better understand the complex systems that operate beneath the waves, we must also develop the wisdom to use this knowledge responsibly. The ocean is not an infinite resource or an impermeable barrier that can absorb unlimited abuse. It is a complex, interconnected system that is vulnerable to human impacts and that requires careful stewardship if it is to continue functioning. In the end, the story of the underwater world is still being written. Each expedition brings new discoveries, each technological advance opens new possibilities, and each generation of researchers builds on the work of those who came before. The ancient cities and hunting grounds submerged by rising seas, the controversial monuments that challenge our historical assumptions, the tragic shipwrecks that hold lessons about human fallibility and political intrigue, the extraordinary deep-sea ecosystems that operate on chemosynthesis rather than photosynthesis, the deep biosphere extending into the fractured rocks beneath the seafloor, the sophisticated behaviors of organisms we once thought simple. All of these discoveries have enriched our understanding and have revealed a world far more complex and fascinating than we could have imagined. As we continue this journey of discovery, as we explore ever deeper into the ocean and uncover more of its secrets, we do so not just out of curiosity, though curiosity is certainly a powerful motivator, but also out of necessity. Understanding the ocean is essential for understanding our planet, for managing human impacts on marine ecosystems, and for addressing the environmental challenges that threaten both the ocean and humanity. The underwater world is not separate from the world we inhabit on land, but is intimately connected to it through the circulation of air and water, through the migration of organisms, and through the biogeochemical cycles that sustain all life on Earth. The mysteries of the deep remain, calling to us across the dark waters, promising revelation to those patient and brave enough to seek them out. The underwater world awaits, vast and largely unknown, holding in its depths the history of our planet and perhaps hints of our future. May we approach it with the curiosity of explorers, the rigor of scientists, the reverence of conservationists, and the wisdom to recognize that what we find there belongs not just to us, but to all life on Earth and to all the generations yet to come.